In this example, we're asked to find and plot the voltage across the 20 kilo ohm resistor, VR, and the current through the 10 millihenry inductor, IL. We're told that the switch was open for a long time before it closes at time 0 and stays closed for 3 microseconds and then reopens. To begin our analysis, we notice that we have 3 time periods. Time period 1, which is before time 0 when the switch was open, time period 2 when the switch is actually closed, and time period 3 once the switch has reopened. We need to analyze the circuit in each of these periods to determine the behavior of the voltage across the resistor and the current through the inductor. And so let's start by looking at time period 1, where t is less than 0. During this time period, you'll notice that the switch is open, and so that isolates our inductor and resistor from the 10-volt source, which means that it's a circuit that has no voltage sources in it, and any current flowing in the inductor will be dissipated in the 20 kilo ohm resistor, and the current will die out to 0 after a sufficiently long time, so we can write that IL in this time period must be equal to 0. Similarly, because there's no current through the inductor, there's no current through the resistor, and so the voltage across the resistor during this time period, VR, must also be 0. Now we'd like to analyze the circuit for time greater than 0 but less than 3 microseconds. In this time period, the circuit does not know that the switch will open at 3 microseconds, so we can just evaluate it assuming that the switch will remain closed for the whole time period. And we'll worry about what happens at 3 microseconds once we have an equation for the current and the voltage. To begin our analysis, we'll just give ourselves a bit more space here. And we know that during this time period, because we're going to have a step response, that our current and voltage will be given by an equation of the form where x of t will be equal to the final value of x minus the difference between the final value of x and its initial value x at 0 plus, all multiplied by e to the minus t over tau. Looking at our circuit, the switch will be closed, so we'll draw the switch in as being closed. We can see that tau is for an inductive circuit, so it'll be L over R equivalent, where R equivalent is the equivalent resistance seen by the inductor. When we do find the equivalent resistance, remember we set our independent sources to 0, so our 10-volt source will be shorted out. Consequently, the equivalent resistance will be 20 kilo ohms in parallel with 5 kilo ohms. And so we'll end up with our 10 millihenry inductor over 4 kilo ohms. If we work that out, our time constant works out to 2.5 microseconds. So that will be the time constant for both the resistor's voltage and the inductor's current. Now we can start to take a look at the inductor's current and the resistor's voltage. First, we want to find the inductor current at the initial starting point, or IL, at 0 plus. Knowing that the current through an inductor cannot change instantaneously, it must be the same as it was at the end of the last time period, or IL at 0 minus, which was simply equal to 0. On the other hand, if the switch has been closed a long time, then IL will eventually settle down to some DC or constant value, and here the inductor will be a short circuit, and you can see now the current through the inductor will be the same as the current through the 5 kilo ohm resistor, because no current will flow through the 20 kilo ohm resistor because there's a short circuit across it, and so the current there will be simply given by 10 volts divided by 5 kilo ohms, which is 2 milliamps. We can now write our inductor current as IL of t will be equal to its final value, 2 milliamps, minus the difference between its final value, 2 milliamps, and the initial value, which is 0, e to the minus t over 2.5 microseconds. We can clean that up, and we can write up here, we'll write it up here so we can put them all together. I of t will be equal to 2 minus 2 e to the minus t over 2.5 microseconds. And our units for this will be in milliamps. Now we'd like to figure out what happens to the resistor voltage, and VR at time 0 plus we can analyze by revisiting the circuit and saying what were the initial conditions. In the initial conditions, when we close the switch, the current through the inductor will be 0, which means all the current must flow through the 20 kilo ohm resistor. Notice that the inductor's current is 0, but we have no specification on its voltage. It will be determined by the rest of the circuit. And we can see that VR will be simply a voltage divider formed by the 20 kilo ohm resistor and the 5 kilo ohm resistor along with the 10 volt source. So we can write that down as 20 kilo ohms divided by 25 kilo ohms times 10 volts will be equal to 8 volts. Then for the value of the voltage across the resistor at infinite time, or when all the transients have died out, we can look back at the circuit and we can see that at the end of the time the inductor will look like a short circuit, and that means there'll be 0 volts across the resistor, so VR must go to 0. Notice we don't think about the 3 microseconds during this time period because we want an equation for what's happening during the time period, and the circuit has no way of knowing if the switch is going to change from closed to open at some particular time. So we can now write that VR at infinity will be 0. Or we can write now that VR as a function of time will be equal to the final value, which is 0, minus the difference between the final value, 0, and the initial value, 8, times e to the minus t over our time constant, and it has the same time constant, or 2.5 microseconds. I can clean that equation up, and we'll put it up here to add it to the other result that we have. VR of t now will be equal to simply 8e to the minus t over 2.5 microseconds. And the value will be in volts. Going back to the top, you can see during this time period the switch is closed, and our equations indicate that the inductor current will eventually head off to 2 milliamps, and the voltage across the resistor will eventually go to 0. During this time period, the circuit is unaware that the switch will open at 3 microseconds. Now we'd like to take a look at what happens 3 microseconds. At 3 microseconds, you'll notice our switch is now open, and we're interested in what happens for 3 microseconds is less than the time, and we want to evaluate what's going on in the circuit. But with the switch open, we're now going to have current initially stored in the inductor is given by the equation from the last period, and that current will flow through the resistor and eventually causing the voltage across the inductor to go down to 0 and the current to decay away to 0. So let's take a look now at how we'll analyze this one. We know all currents and voltages in our circuit will be of the form x of t is equal to the final value minus the difference between the final value and the initial value multiplied by e to the minus t over tau. Once again, we'll start by looking at the time constant, which we know is L over the equivalent resistance. And in this case, the equivalent resistance now has changed because the switch is now open. Now the 10 millihenry inductor only sees the 20 kilo ohm resistor, leading us to a time constant of 0.5 microseconds. We note that the time constant has changed between the two periods. That's because the circuit has changed, and so the equivalent resistance seen by the inductor has changed. A very important point here. Looking now at the current, we want to find what IL at 3 microseconds on the positive side is equal to. Well, we know that that will be equal to the inductor current at 3 microseconds on the minus side, and that will be simply equal to 2 minus 2e to the minus 3 microseconds divided by 2.5 microseconds, which gives us 1.4 milliamps. And that becomes our initial starting current. Notice that in the last period it thought it was headed off to a total of 2 milliamps, but it never got there. At the end of this period, the inductor current IL at infinity, we can see will eventually settle out to 0. So if we take these two facts and combine them, our inductor current will be, as a function of time, will be equal to the final value, which is 0, minus the difference between the final value and the initial value, times e to the minus t over our time constant, tau, where we can substitute in the values and see that we'll have 1.4 e to the minus t over 0.5 microseconds, and that will be in milliamps. The current will simply decay away from 1.4 milliamps to 0. So we can write that current up here, I of t will be equal to 1.4 e to the minus t over 0.5 microseconds, and that's in milliamps. Lastly, we want to find the resistor voltage as a function of time. To begin, we want to find the resistor voltage at 3 microseconds on the positive side. At 3 microseconds, our switch opens, but our inductor still has current in it, flowing down through the inductor, and it will be forced to flow back up through the resistor. We know from the above analysis for the current that the current was 1.4 milliamps right at this point in time, and that will be flowing through the resistor, so the voltage across the resistor now will be equal to the resistor, 20 kiloohms, times the current through it, 1.4 milliamps. But note that the current flows in the opposite direction to the way that we've labeled the voltage, so it will be minus or minus 28 volts. Rather a large voltage, but we won't worry about that. Lastly, we need to find the resistor voltage at infinity when all the transients have died out. And because the circuit here has no extra power sources in it, all the current in the inductor will be dissipated in the resistor, and the resistor voltage will decay to 0. VR as a function of time will be equal to minus 28 e to the minus t over 0.5 microseconds, and that will be volts. We can write this equation up here to keep track of that one. Minus 28 e to the minus t over 0.5 microseconds. And that completes the analysis. Now we'd like to plot the current and voltage as functions of time. We'll begin by plotting the current. So I of t, we'll put a timeline across here. We want to plot the current versus time. Before time 0, our current will be 0, so we'll put 0 current down here. But at time 0, it's going to follow the second equation, 2 minus 2 e to the minus t over 2.5 microseconds, which means it starts out at 0, 2 minus 2 is 0. But over time, it will eventually want to rise up to 2 milliamps. So we can put a dotted line on where we think it's headed after a sufficiently long period of time. It's going to take 5 time constants to get to within 99% of the way there, or after our first time constant will be 2.5 microseconds, will be approximately two-thirds of the way there, so we'll be somewhere around here. And by the time we're at our second time constant, or 5 microseconds, we'll be another two-thirds of the way, and so on. And so our graph will look approximately like this, and it will converge. Now I haven't filled in a solid line because we know at some point in time it stops following that curve. And we know that that happens at the 3 microsecond mark. At 3 microseconds, our graph will stop, and so our current will follow the equation for this time period until we get to 3 microseconds. But at 3 microseconds, when we will be at 1.4 milliamps, all of a sudden the equation changes to 1.4 e to the minus t over 0.5 microseconds, which is a decaying exponential, and its time constant is only half of a microsecond. Well, I want to have 5 time constants in here. If I have 5 microseconds on there, that'll be 4. So my first time constant is right here, second, third, fourth, fifth. So by the time I get to that mark there, that will represent 5 tau for t greater than 3 microseconds. And in this case, my curve is going to be very steep and come down just about something like this, and then stay at 0 for the rest of the time. You can see that it rises slowly, the current rises slowly, and then it drops off very quickly once the switch changes. Let's take a look now at our voltage, VR, as a function of time. Now this one, taking a look at where we are, we're going to start at 0. It's going to jump up to 8 volts and then decay down to 0. But before it is decayed all the way to 0, it's going to jump down to minus 28 and then decay back up to 0. So let's draw our graph on here, and we'll put something that looks about like this now. Again, we'll have time on this axis, and we'll put our voltage on this axis. Before time 0, our voltage across the resistor was 0, so we'll label that as 0, and at time 0 it jumps up to 8 volts, at which point it wants to decay away, hopefully to 0, and so we'll draw it decaying away to 0 in about 5 time constants, where the time constant is 2.5 microseconds, and so it will follow this line until we get to the 3 microsecond mark. At this point we switch to this new equation where it says that our voltage drops to minus 28. We're going to go down all the way down to minus 28, where our current now will decay away to 0, but with a much faster time constant, and look something like this. That completes our analysis. You can see that the current through the inductor is continuous, starting at 0, then rising slowly up, trying to get to 2 milliamps, but before it gets there, the circuit changes and it decays away back down to 0. On the other hand, the voltage across the resistor starts at 0, jumps up to 8 volts, it's discontinuous there, then it decays away towards 0, but before it gets there, the circuit changes, it drops down to minus 28, and then it decays away back to 0 again. And that completes the analysis of our circuit.